Assalamualaikum warahmatullahi wabarakatuh. So my name is Muhammad Izzat bin JAMIRUDDIN. My metric number is DD23031. So I'll go through for the introduction slide, which is in this project we will do evolution from manual to automated water level control system using integration of feedback control of principal engineering applications. So the challenges in controlling non-self-regulating dynamic system I will explain in this project, and then we will take the importance of PID control in water level regulation, and then we develop and performance evaluation of the proposed control system, and then the implementation of Arduino based hardware and sensor integration also take in this project, and then we will know real-time monitoring, control action, and safety features for this project. Due to industrial significance of PID-based water level control system.
Hello, my name is Muhammad HAMIZI bin NORHISHAM, matrix number CD240157. Today I will continue this presentation about the aim and objective of the project. The main aim is to design a closed-loop water level control system using Arduino and a PID controller. In this project, a hardware and software integrated system is developed to control the water level automatically. The PID controller is applied to maintain the water level at desired set point. Then, the system performance is analyzed in terms of response, steady state error, and stability. Finally, the system is validated using MATLAB or Simulink, and the results are compared with experimental data.
Assalamualaikum, my name is UZMA, and right now I will presenting about the literature review. So, this project focuses on a water level control system which is commonly used in domestic and industrial applications to maintain the desired water level and prevent overflow. To achieve accurate control, a PID controller is implemented. PID stands for Proportional Integral and Derivative Controller. It is widely used in industrial automation because it provides stable and reliable system performance. In this project, a soil moisture sensor was used to simulate a water level sensor because Tinkercad does not provide a dedicated water level sensor. The sensor continuously provides feedback to the controller for monitoring and control purposes. Right now, I will present about the theory. So, the PID controller calculates the control output based on the error between the desired water level and the measured water level. The error is calculated using the equation set point minus process variable. The proportional gain Kp increases the response speed of the system. The integral gain, which is Ki, it reduces steady state error and helps the system reach the desired set point. So the derivative gain, which is Kd, improves stability by reducing oscillations and overshoot. In this project, the proportional gain was fixed at 0.5 and the derivative gain was fixed at 0.2. Different values of integral gain were tested to investigate their effect on the water level response and overall system performance. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad IZWAN HAIKAL bin KAMARULZAMAN and my matrix number is CD230286. So I will continue this presentation about the apparatus. This project is designed to monitor and control water level using an Arduino based system combined with PID control principle. The hardware consists of an Arduino Uno as the main controller, a soil moisture sensor connected to analog pin A0, a 16x2 LCD display, an LED indicator and a buzzer alarm. These components work together to provide real-time monitoring and warning functions. The sensor measure the water level and sends an analog signal to the Arduino. The Arduino convert this signal using its 10-bit ADC, producing values from 0 to 1023. Based on this reading, the system display the water level and activate different alarm states. When the reading is 500 or below, the buzzer remains off. Between 501 and 800, A slow beep is activated as a warning. Above 800, a fast beep indicates a critical water level condition. So the next slide is experimental method. MATLAB Simulink is used to create a closed loop PID control system. The proportional gain Kp is fixed at 0.5 and the derivative gain Kd is fixed at 0.2. Meanwhile, the integral gain Ki is tested at three different values: 0.005, 0.02 and 0.05. The water tank is modeled as first order transfer function and the system response is observed using a score block. The performance is evaluated by comparing rest time, setting time, overshoot and steady state error. The results show that increasing Ki improves error correction speed but can cause overshoot. Among the tested value, Ki 0.02 provide the best balance between fast response, low overshoot and stable water level control. Thank you.
Okay, for result and discussion, our PID controller successfully regulate the water level in both simulation and real experiment. The proportional term provides a fast response while the derivative term ensures stability with very little overshoot. The integral term play a key role in minimizing steady-state error. Overall, the best performance were achieved by Kp equal to 0.5, Ki equal to 0.05 and Kd equal to 0.2, giving us excellent set point tracking and smooth response. Finally, the simulation and hardware result mesh well, successfully validating our project objective, with only minor difference due to real-world factor like sensor noise. For the response graph from MATLAB, let's look at the figure 7.4, which show the PID controller output or the controller effort for the different tuning sets. As we can see, all three curves start with a high output of around 250 to 255 PWM. This aggressive effort quickly drive the system to the desired set point. As the error decreases, the control signal smoothly reduces and stabilizes at about 70 to 80 units. Notice that the response with higher KI is set at a slightly higher steady-state value, which makes sense because stronger integration is needed to keep the water level closer to the set point. The smooth decay without oscillation shows how good system stability is. Now, moving to figure 7.3, this graph displays the error response for the three different KI values. All response show a rapid initial drop in error. However, with the lowest KI of 0.005, the error decreased slowly and leaves the largest steady-state error of about 130 units. In contrast, higher KI value of 0.02 and especially 0.05 reduce the error much faster and achieve significantly lower residual offset, down to around 60. This clearly validates the important role of the integral term in eliminating steady-state error. Importantly, there is no oscillatory behavior thanks to the effective damping provided by our KD value, which is 0.2. Next, let's start with figure 7.1, which shows the water level response for three different integral gain values by keeping Kp at 0.5 and Kd at 0.2. All the all the three curves show a fast initial rise, which indicates strong proportional action. With the lowest Ki of 0.05, the water level settles around 570, leaving a noticeable offset from the set point. As we increase Ki to 0.02 and then to 0.05, the steady state level improves significantly, reaching about 595 and 644 respectively. The highest Ki value give us the best set point tracking with the smallest error. Although it's slightly more aggressive at the beginning, there is no major overshoot or instability. This clearly shows that increasing the integral gain effectively reduces steady-state error as expected from theory. Now, for the figure 7.2, represent the best performing PID parameter, which is Kp equal to 0.5, Ki equal to 0.05, and Kd equal to 0.2. The blue curve shows the water level rising smoothly and settling very close to the set point with minimal overshoot and a settling time of only 10 to 12 seconds. The orange curve represents the pump output, It starts high to correct the error quickly, then decrease smoothly to a low value to maintain the level. This demonstrates excellent control action, strong initial effort followed by efficient steady-state operation, and confirms that our PID algorithm works well in both simulation and on the actual Arduino hardware.
Now, I will close this presentation with present about conclusion this project. This project successfully designed and implemented a water level control system using an Arduino Uno and a PID controller. The system integrates both hardware and software components such as a sensor, LCD buzzer, and LED. The results show a strong agreement between simulation and experimental data, which validates the accuracy of the system. Any minor difference observed were mainly due to sensor limitation. The PID controller proved to be effective for controlling non-self-regulating system. Overall, this project provided useful skill that can be applied in industrial automation, process control, and mechanical engineering. Thank you.
This is water level sensor circuit shown from Tinkercad, and it shows all the connection from the Arduino Uno to breadboard to the LCD to buzzer and then to the sensor. It shows when the water level is decreasing, the buzzer will beeping faster.